Hey everybody, Chris from FlipMath, and I'm going to take you through today's lesson, which is on integration, and I've called it Everything You Know Backwards. It's a C2 module, part of the AS Maths course, although for other boards it's a C1 module. I teach it from a C perspective, but it should be applicable to all boards. The objectives are very simple. I'm just going to teach you to integrate by rule in this lesson, so how we go through the process of integration and the formula for it, etc. etc. Introduction is this. So, the last topic that, or not the last topic, the topic that this links on to, is differentiation, part of the calculus thing, and it's a core subject which we've already covered in probably a lot of detail in some stage. We're done with it, right? Kind of. Integration links onto it, and you should be able to differentiate by rule before you come to integrate, although strictly speaking I suppose that's not 100% true because they're two separate operations. But to understand what's happening, it'd be good if you understood what differentiation is. So what is it, integration? So it's the opposite, or as we like to call it in maths, inverse operation of differentiation. So that is, if I supply with the expression for the gradient function, which is what you get when you differentiate, can you find the original curve or the original expression that it comes from? You're your own greatest teacher. You're the best teacher in the world. So much like what I did when I was going through the differentiation, I'm going to see if you can spot it yourself. So differentiate each of the following and then examine the results. So can you produce the results for integrating yourself? And I'm going to pop them down here. So I've got y equals x squared, y equals 3x squared plus 4x, y equals 4x to the 4 plus 2x cubed minus 2x, y equals 3x cubed plus 6x, and y equals minus 6x plus 4. So they're just 5 things that are fairly straightforward to differentiate. And you can pause the video, and this, like I said, if you can, you should be able to differentiate by rule to be able to do this. If you haven't done that, go back and watch that video. If you've done that, you should get the following. For dy by dx for the y equals x squared, you should get 2x. For the 3x squared plus 4x, you should get 6x plus 4. For this, 4x to the 4 plus 2x cubed minus 2x, you should get 16x cubed plus 6x squared minus 2. For y equals 3x cubed plus 6x, the differential expression for that is 9x squared plus 6. And finally, for y equals minus 6x plus 4, you should get y equals just minus dy by dx equals minus 6. Okay, and I'm going to step you through each of these and we'll have a look. So what patterns can you see? You might find that some fit your pattern and some don't. That's fine. Any good engineer or anybody who's trying to solve any problems will tell you that if you know part of the solution, you're part of the way along developing the whole solution for yourself. And it's a great starting point because whenever you're testing theories, you change the variables as you go along and test them for various solutions to see if you can just tweak it a little bit to see if it can work. So let's look at each of these in order. If I look at the y equals x squared that gives us dy by dx equals 2x, what ideas might you have generated? I'm thinking you may have said that the number in front becomes the power, if you don't know, or the number at the end becomes the bit in front when you do it. So that goes to the front there. We'll see if that works. So we'll look at the second one. And we'll see, we'll see that this doesn't work, as that would be 3. On there would be x to the 6, and that's not what it is. Or sorry, that'd be x to the 6. And that's 3x squared is what we've got here. And the 4, well, doesn't really work. However, the 6 does get broken into 3 and a 2. Interesting. The plus 4 becomes 4x, which should be surprising. I should probably remember that differentiating the next term, the x disappears. So when you differentiate a 4x, you just get a number. So if you see a number and you were going to do the backwards way of it, you mightn't be surprised to say, oh, you just stick on the x back on. If I look at the next one, we're starting to get there. The 16 becomes 4 and 4. So again, the 16 becomes the two factors of it, and the last one, the 6, became a 3 and a 2, which were factors of the 6. And this one, the 16, becomes a 4 and a 4. You should also notice that the 3 becomes a 4 here, okay, and the 2 becomes a 3. So, by now you might have seen that when we integrate, we increase the power by 1, so the 3 becomes a 4, the 2 becomes a 3, etc. and then we divide by the new power. Now you may have not have seen this second step, but it'll be more clear as we go along. So we can check this with our next example. I'll go back to the previous one as well. So if 9x squared plus 6 was our original differentiated expression, so I'm going to increase the power by 1 here, so that'll be x to the 3, and then I'm going to divide by the new power, which was 3, so I'm going to divide by 3. So we should get 9 over 3 x to the 3, and 9 over 3 gives you 3. So increase the power by 1, x squared becomes x cubed. Divide by the new power, 9 becomes 9 divided by 3, which is 3. So 9x squared, when we integrate, becomes 3x cubed. And again, we can add the x back on, but if we're going to integrate, 6 is really 6x to the power of 0, because x to the power of 0 becomes 1. We increase the power by 1, so it becomes x to the 1, divided by 1, that just becomes 6x. I can take you through that in a bit more detail in class if you want, but for many cases, most people, when they're integrating, just know when you get a number term, put an x in the front, or whatever you're integrating with respect to, and we'll come to that in a second. That's integrating by rule. I mean, if I show you this bit up here as well, the x to the 3 becomes x to the 4, and then we divide by 4. So 16 divided by 4 gives us 4, x to the 4. X squared becomes x cubed. We divide by the 3, 6 divided by 3 gives us 2, and the minus 2 just gets the x in front. That's integrating by rule. Okay, so let's go through the process in a little bit more detail and examine the two of them. So when you're differentiating, you start off with an expression that links y and x, or two variables. To differentiate, you multiply by the power and reduce the power by 1. So you multiply, but if it's x squared, you multiply by the 2, and then you reduce the 2 to become 1, so that becomes 2x. And that gives you your gradient function. When you integrate, you start off with the gradient function, and like we said before, when you're going backwards, you increase the power by 1, which kind of makes sense, and then instead of multiplying by the power, you divide by the power. So all the inverse operations of what we did beforehand, and you'll get your expression. And if you want to write that down for yourself in some way, that's usually the way that it goes. So there's a few things. I'm going to look at some of the notation involved that you get, and instead of words, there exists a formula that says the same thing. So for an expression of the form dy by dx equals ax to the power of n, where a is a number and n is a number, we obtain the integral by ax to the n plus 1 divided by n plus 1. So we increase the power by 1, we divide by the new power, and that's all it said. I'm also going to introduce you to the integral symbol itself. That's what it looks like. Some people think it looks a little like its long lost cousins, the treble clef and the bass clef. If you're a musician, many years of playing the clarinet and saxophone, etc., tell me that that's a pretty astute observation. I suppose in many ways calculus is very much like music. It's beautiful and tuneful and wonderful if you can make it work for yourself, and if you can't make it work for yourself, it just sounds goddamn awful. The symbol by itself does not make an integral, however. You need a variable with respect to, so just that symbol by itself isn't an integral. And again, when we come to C3, C4, I'll ram this home. That in front of a function or expression does not make an integral. An integral is something with respect to another number, and the dx or the dy or the dt or the whatever is the end tells you what you're going to integrate. So in this one, I'm going to integrate with respect to x, meaning that I'm only going to look at the x terms. If there's any y terms and stuff in it, you'll ignore them at a certain point. Okay, so for instance, if we integrate the integral of 2 with respect to x, we would just integrate the 2 and would put an x in the end. Whereas if we integrate a 2 with respect to t, we're going to put a t in the end, because the variable we're talking about is t in this one. In this one, it's x, and we put an x in front. If it was 2 d theta, it would be 2 theta, etc. You'll investigate this more while studying C3, like I've just said. You may have also noticed that I did not step you through the last of our expressions, or our last of our differentiation problems. I'm going to have a look at that one now. When we differentiated the expression at the start, we got that the gradient function, or the differentiated function, was minus 6. Using our new notation, that would be the integral of minus 6 with respect to x, and when we integrate that using the rules, would just increase the power of the x by 1 and divide by the new power, or with just a number, we put an x in the end. But as our original expression wasn't like that, it was minus 6x plus 4. And one of the problems is it's like the mat plus 4 never existed. This is known as an indefinite integral because when we had this differentiated expression at the start, we couldn't know exactly what the whole thing was. We got part of it, sure, we got the minus 6x, but we never got the plus 4, and there's no way, without some more variables or expressions, that we could have known that there was a plus 4 there. We call it an indefinite integral. And the next lesson will come to definite integrals. We'll look at those next lesson, but for the moment we're going to show you the way that we deal with it, or we notate it. It's not really that you're dealing with it in any way, but you need to include another term. If we differentiate a constant, a number, it disappears, remember? So when we integrate, we must represent this possible number in some way, and the way that we do it is we must put a plus c, or what we call plus a constant. So there could be a number there. We just don't know. We'll say plus something. We'll call it a letter, because we'll like that maths when we get to a certain point, don't we? Like using letters. Everyone forgets to put it at the end. However, it is wrong without it. You will lose at least 1 mark for it. And I've done it myself in my own studies of, especially as integrals get more and more complicated, the less that you remember to put the plus c in. And it's very key that you do. So common is the epidemic of forgetting the plus c that entire companies have been formed out of it. People make stamps so that teachers can go around and go plus c, plus c, plus c, plus c, etc., etc. In fact, if all goes to hell with my teaching career, I might just start up one of those companies myself. Start up the plus c company. Let us look at a number of different integrals before you attempt many more yourself. So I've obviously got exercises on the site and in class for you. So example 1, we're going to evaluate the following. The integral of x cubed minus 3x plus 4 with respect to x. And all of these are going to be with respect to the variable that we've got inside there. Again, when we come to C3, C4, you'll do it slightly differently. We'll treat each term individually and remember a two-stage process. Increase the power by 1 and divide by the new power. So our x cubed becomes x to the 4, and then we'll divide by the 4. Okay, so increase the power by 1 to become 4, and divide it by the new power, which is 4. So that's the same as x to the 4 over 4, or a quarter x to the power of 4. Next one is minus 3x. We increase the power of x by 1, so this was a 1, it becomes a 2. And then we divide by the 2 as well, so it becomes minus 3 over 2 x squared. And the last one is plus 4. Well, the plus 4 becomes plus 4x. We put all our terms together. The x cubed became x to the 4 over 4. The minus 3x became minus 3 over 2 x squared. And the plus 4 became plus 4x. And that's it. Or is it? Bet you forgot the plus c when you were going through them. And I put it in red so that you would not. But like I say, especially when you're starting off, you'll find me going around writing the plus c on your paper an awful lot. Example 2. Evaluate the following. 2x to the 5 plus 3 over x squared with respect to x. Training wheels are off already. We're going to increase the power by 1 for each and divide by the new power. Well, the 2x to the 5, we're going to increase the 5 to become a 6, and we're going to divide by the 6, and 2 over 6 becomes 1/3, so that becomes x to the 6 over 3. The 3 over x squared, we're going to have to change. We got to write it in indice notation. So 3 over x squared becomes 3x to the minus 2. Minus 2 when we increase by 1 becomes minus 1. And we'll divide by the minus 1. 3 divided by minus 1 gives me minus 3. And x to the minus 1 becomes 1 over x. And we generally write it like that. Although in many cases, the answer will be acceptable still left in indice form, with just tidying up the 3 divided by minus 1 to give us minus 3. So minus 3x to the minus 1 would also probably be acceptable for many answers. So our answer is all that put together. So x to the 6 over 3, minus 3 over x, not forgetting your plus c. And that is our lesson. Next time on integration, we're going to find the difference between definite and indefinite integrals and use integration superpower to find the area. And you're going to see why integration's a powerful tool. So our objectives were to integrate by rule. Hopefully we have attained that. If you have any questions, you can come back to me in class or over Twitter, as you'll see. Practice, practice, practice. For exercises, solutions, quizzes and downloads around the subject, go to flipmath.co.uk and search for integration. Feedback on all resources should be sent to flipmath at flipmath or in the comments to this video. I'll pick them up. But until then, thank you for watching. I'll catch you next time. Bye.